All right, folks, up until now we have been talking about ketones and aldehydes, and they've been having all the fun with the aldol formation and the aldol cyclization. Today we're going to talk about esters in the same situation. The principal difference in what happens now depends on two factors. One, this is base only. In fact, the base has to match the alcoholic portion of the ester. And two, it relies on the fact that esters undergo carbonyl substitution reactions rather than addition. All right, now let's take a look. So let's say we've got, I love this one, I use it all the time, ethyl acetate. A couple of fun facts about ethyl acetate. It is currently the primary ingredient in nail polish remover. It used to be acetone, then they decided this was a little better because, one, when it hydrolyzes in nature, it turns into acetic acid and ethanol, things that the universe knows how to deal with fairly well. The second reason that this is an interesting molecule is ethyl acetate is as polar as you can get without being water soluble. So there are plenty of more polar solvents than ethyl acetate here, but they're all water soluble, methanol, ethanol, etc. So what we're going to do is we are going to react our ethyl acetate here with ethoxide. Once again, this portion of the molecule has to match here. Otherwise, you get into a big mess of esters you form in the end. All right, so here we go. Here's what your product would look like. All right, there's your product. This is the aceto, well, in this case, it's an ester, but you get the idea. The key thing here is you now have two protons in the middle that are fairly acidic. So really, your product would look something like this until you chose to throw a little acid in there just to shut it up. Okay? Here's how this works. Oh, let's say this, and we've got this anion, pull off the proton, swing down from pi bond, open up the carbon-oxygen pi bond, and you are here. Now, again, there's no other nucleophile in here. You could theoretically alkylate this way. I don't know that I've seen many people do it, but you could. And so now you're at this point. There is the other ethyl acetate, nucleophilic attack, open up the pi bond. So we're here. O minus. And that extra methyl group. This is where it being an ester comes into play. Reform the carbon-oxygen pi bond, knock off the ethoxide group there, and you are here. And just for completeness purposes, that ethoxide that you just knocked out would actually be doing this. Because that's a fairly acidic proton. But, you know, add some hydrogen there, a little acid from someplace, and you get this. Now, here's the thing, folks. I'm kind of open about these things, really. I tend not to be too terribly picky. So this works in mono Clasiens. Like we had aldol in the last case, this is called a Clasien reaction. So let's take a look at a cross Clasien, where you use two different esters. So let's say here, and there. All right. Now, I picked this for a reason. This ring, no alpha protons. So it cannot do enolate chemistry. Where this ester, the ethyl acetate over here, can, and we react this with ethoxide. Here's the mechanism for it. We form the enolate off of our ethyl acetate, and we don't have to worry about it over on the aromatic side because there's no alpha proton there. So we're here. Now we bring in this other ester for us to play with. Skipping a couple steps, and we get here. This is the only time a crossed Clasien actually works, is when you've got one of the esters has alpha protons and the other one does not. Otherwise, if you did methyl acetate and ethyl acetate, you get a big mess of products. Now, this proton, again, is fairly acidic and can be pulled off by the ethoxide you just used. All right, will this work for cyclizations? And the answer is yes. Let's see how. So let's take a look at how these esters do cyclize. Let's start with something like this. 1, 2, 3, 4, 5, 6. See what I mean, folks? I count carbons, so can you. They just won't let me into organic Vegas for that. So what we do is we react this with ethoxide. Your product would look... That is the lamest six-membered ring I have ever drawn. Let's try that again. Slightly better, although not a whole lot. There. Now, let's examine how that happens. Two, three, four, five, six. We had the ethoxide pull off the proton. I'm not going to show it to you because it's the same thing we've done a million times. Nucleophilic attack. Open up the pi bond, close the pi bond, knock off the leaving group. So you wind up here. And of course, this proton is removable with the base. Now let's talk about why these ester ketones are interesting. And let's do a simple one. So there is the Clasien condensate product we get of reacting ethyl acetate with ethoxide. All right, all is well with the world. We can do all kinds of crazy shit to that middle carbon, as long as it can be done through the base pathway. So why don't we just go ahead and attach our crazy shit right there. Then what we can do is we can turn that ester into a carboxylic acid. So let's say acid and water, and what we've done is we have turned our carboxylic acid, we have turned our carboxylic acid, we have turned our ester, rather, into a carboxylic acid. Now, we decarboxylate this. High heat. Where did any of that come from? Sorry, got distracted. Loud kids. Okay, let's change that to this. Crazy shit there. All right, now we decarboxylate this, and here's what we have. This is how we get well-substituted ketones. All right, that's all for today. Tomorrow I will make a few videos reviewing the alpha-beta unsaturated carbonyls and all the fun type of chemistry we can have with those. So, ladies and gentlemen, I hope you're doing well. Stay healthy, stay safe, stay hydrated.